Okay, evolution makes trees. What do those trees look like when you put them into the full context of Earth history? Well, we're not going to finish this today, but in such time as we have, let's look at yet another dead white dude whose name you really ought to know because he's kind of a founding father of geophysics by the name of Alfred Wegener. He was German. Had the kind of brain that doesn't neatly fit into any one category. Brilliant man, did pioneering work in atmospheric science. He was one of the first to put weather instruments on balloons, for example, for measuring conditions in the upper atmosphere. Did a PhD project that was actually in astronomy. Was involved in polar exploration. That picture of him was taken in a little hut on the Greenland ice cap. In fact, he died on a polar expedition and is lost somewhere on the Greenland ice cap. Which probably means he'll be floating into the Atlantic in a couple of years, the way things are going. And he got interested in this weird possibility that the Earth's continents, as big as they are, might not actually stay in the same place permanently. And he got his idea while reading about what we now call biogeography, which is just the study of the distribution of animals and plants. He hypothesized that a long time ago, let's say about 250 million years ago, the continents of the Earth were joined together in a single one called Pangaea. Obviously, there weren't people back then, so we have no way of knowing what the the synapsid theropods called it. They probably didn't have a language. We now call it Pangaea. Gaea is, of course, Earth. Pan is Greek for all. So Pangaea is all Earth. And the continents were separate before then. We're not going to get into where they were. That's another kettle of ballgame. But they came together about 250 million years ago to form Pangaea. And Pangaea began breaking up roughly 200 million years ago. What that created was a northern half called Laurasia. Laurasia consisting of Europe, most of Asia, and North America. And a southern half called Gondwana, consisting of Africa, South America, Australia, New Zealand, Antarctica, and a few other fiddly bits like India. India used to be part of Gondwana. It was an island for a while, and it has recently crashed into Asia. So, India's gotten around. And yes, that is why the Himalayas are the tallest mountain range in the world. That's where India's been colliding with Asia and is still getting shoved northwards. And then both of those halves, over the next millions of years, fragmented further and ultimately gave rise to the continents we now have. And it sounds like a nutty idea because continents are so big. North America is 3,000 miles across and averages something like 25 miles thick. That's a lot of rock. And it doesn't seem like the sort of thing that should be able to move. And yet Wegener kept looking at the distribution of fossils that would have lived around the time that Pangaea was breaking up. What you're looking at here are leaves of a fern-like plant. It's technically not a fern. It had seeds for one thing, and it may be fairly close to the origin of flowering plants. It's called Glossopteris. And I have personally found fossils of it in Australia. There's a leaf venation pattern that is hard to miss. It's also turned up in India, not shown, but it has turned up in South America, and it's even been found in rocks in Antarctica. Antarctica is mostly covered by ice for now, but the bedrock that is exposed includes rock layers that do contain fossils. Antarctica was not always completely covered by ice. And some of those fossils, dating between about 290 and 255 million years, include these Glossopteris. Okay, so what? That's just one. Round about the time Pangaea existed, there were type of land animals called synapsids. They used to be called mammal-like reptiles, although we shouldn't call them that. They're not really reptiles. They included ancestors and close relatives of modern mammals, although they themselves are not fully mammalian. They've got some mammal features, but not all of them. One that you may be able to see in those pictures is they've got different shapes and sizes of teeth. As opposed to something like a crocodile or a dinosaur where the teeth are pretty much all the same. These were evolving incisors and canines and molars and such.
So they lay eggs or?
Oh, God, you had to ask. They probably still laid eggs, and I mean, for that matter, the earliest branches of the mammals to branch off still do lay eggs, platypus and echidnas. So they probably were egg layers. What they are evolving is a much more upright posture, less sprawling of the legs like you would see in a gator. Starting to develop the zygomatic arch, that's a cheekbone basically. It's this. Beginning to lose ribs in the abdomen, that probably correlates with the evolution of a diaphragm, which is another thing that mammals have that non-mammals don't. These happen to be just two different genera of synapsids. Cynognathus on the bottom would have been a relatively fast, almost dog-like predator. Lystrosaurus on top just had a pair of tusks and probably grubbed in the soil for roots or something. Lystrosaurus is kind of weird. And those are living at about the same time frame as Glossopteris. So is this odd little reptile that evidently swam called Mesosaurus. And this map shows where the fossils have actually turned up, superimposed on a reconstruction of southern Pangaea. They're not all found in exactly the same spots, but notice how they overlap. Glossopteris turns up in Australia, Antarctica, India, Africa, South America. Mesosaurus and Cynognathus have turned up in South America and Southern Africa. Lystrosaurus in Africa, India, and in Antarctica. Again, 98% of Antarctica is covered in ice, but there are places where the bare rock is exposed and you can find fossils there, and people have. There were dinosaurs in Antarctica once, although these fossils are just a tiny bit older than those. But yeah, there are Lystrosaurus that have turned up in Antarctica. So how do you explain that? Any one of those you could say, okay, the continents have always been separate and maybe seeds of that fern, Glossopteris, just drifted across the ocean. And that can happen. We can see that today. There are tropical seeds now that will ride on the Gulf Stream all the way to Scandinavia from the Caribbean. So maybe that happened back then. Okay, maybe. But why should you get the same distribution pattern in Lystrosaurus, which is this fairly large, clunky mammal relative that doesn't look like it can swim? why would you get the same or at least an overlapping pattern of distribution with those? You can find the same kind of distribution if you look at living organisms. And there's a lot of them that look like they would have once been unique to Gondwana, Gesundheit, to Gondwana, that southern half, or Laurasia, that northern half. On the left is a plant in the genus Nothophagus, aka the southern beech. And you can find Nothophagus today growing in southernmost South America. You can find it growing in New Zealand. You can find it growing in parts of Australia and in New Guinea. And if you look for fossils, you can find it growing, or remains that it used to grow, in Antarctica as well. These places are now separated by thousands of miles of rather rough polar ocean. How did Nothophagus get there? And why those continents and not any of the others? Well, maybe the seeds floated. How did the lungfish get from Africa to Australia to South America? Lungfish are a small but very distinctive group of fish where the swim bladder is a lung that's connected to the outside world and can breathe atmospheric air. Sorry, I was just reminiscing. I visited Chicago in 2015, and the aquarium in Chicago had an Australian lungfish that was still alive when I was there. He was just kind of sitting there. That's the one at the top right, the Australian lungfish. And I mentioned this because they built the aquarium for, I think, the 1933 World's Fair. And my great-grandfather had visited Chicago and seen the World's Fair and saw that lungfish. Like, I saw a fish that my great-grandfather would have seen. They live a very long time. The Australian lungfish actually just died a couple of years ago. I actually felt a little bad, you know, because I've seen it alive, and you know, this man I will never know had also seen it alive when they built the aquarium, almost 80 years prior. Anyway, lungfish are so dependent on breathing air that they are the only fish I know of that can drown. If they do have gills, but it's not enough to keep them provided. They're not fast swimmers at all. They mostly just kind of lunk around on the bottom. And there's a lungfish species in Africa. There's one in Australia. And I took that picture below. That's also in Chicago. That's a South American lungfish. And they don't just all breathe air, they've got common skeletal structures and things like that. What are they doing only on those 3 continents? They're not likely to have swum because they're all freshwater dependent, and they're not built for crossing oceans. They're built for just kind of hanging out on the bottom. You know, if they were tunas, they could do it. Those are high-speed, long-range cruising fish, but not lungfish. How'd they get there? For that matter, why do South America, Australia, New Zealand, Antarctica in the case of fossils, and sometimes Africa, why do they share conifers in the family Araucariaceae? Things like the monkey puzzle tree and the Norfolk Island pine. Why do they also share ratites, birds with a flat breastbone, ostrich, rhea, mola, elephant bird, now extinct? Why do they all share flowering plants in the family Proteaceae? Like at the top left, Protea, that's the national flower of South Africa. And then an Australian Protea at the bottom left, and a South American one at the top right. Are there families of earthworms that are only found on those continents and those alone? Wegener thought the simplest explanation would be that those continents were all connected. Sure, you could use something like floating seas to explain a few of those cases, but surely that's not going to work for lungfish and flightless birds and earthworms. Those aren't going to float or swim across miles of ocean. Incidentally, Darwin had noticed some of these, and he and others in the 19th century had speculated about the possibility of land bridges, that continents that had always stayed more or less where they were, but at some point there had been dry land making connections between continents so that land animals and plants could disperse. And there are cases where that does work, and we'll see some in probably on Monday. The problem is that to explain all of this, you have to put in so many land bridges in the past that you start running out of room for the oceans. And it works for Laurasia as well. We've hypothesized that North America, Europe, and most of Asia, including China and Russia, were all once part of a single continent called Laurasia. And just as Gondwana has Proteaceae flowers and Galaxian mud minnows and ratite birds and lungfish, the Laurasian continents have oaks, they have sequoias, California redwoods, and Chinese dawn redwoods, and incidentally, fossils in Europe. They have bears. And in this case, they have flowering plants in the family Cornaceae, which you know very well because that's the dogwoods. And if you've ever hung out close to the rivers, it's the tupelos as well. So up there at the top left, that is Cornus florida. That's the flowering dogwood. We've got one just outside the nearest exit to the building. You might have seen it flowering nicely in March. At the top right, there's an Asian dogwood. There's a European dogwood that's not really a tree, it's a little bog plant. But yeah, all three members of the same genus, and all of them found in continents that, according to Wegener, must have been joined together. Maybe seed dispersal could explain how you got dogwoods on these different continents, but it's sure not going to work for bears. You know, bears are not going to go ballooning through the atmosphere until they drift onto new continents. Bears don't really do that. So the only factor that would explain all of this, Wegener thought, was his hypothesis that the continents had been joined. Well, what else is there? Wegener found some geological features that are now on separate continents, but if you put the continents back together, that actually match up. Much like if you found pieces of a broken china plate, maybe flung against the wall of the White House dining room or something like that. You could try to fit them back together based on the edges, but you would also find that if you got it right, not only would the edges fit, but the design on the plate would fit, right? Like a piece of plate that has half of, I don't know, my grandmother always had china with these pretty blue flowers. So you find a broken piece of a plate with half of a pretty blue flower. If you can match it with the other broken piece, then not only will the edges match, but the pretty blue flower parts on the opposing pieces will match. Same thing going on here. You can find mountain, like, oh, here's a good one. We have the Appalachian Mountains running up the east coast of the US. If you push North America back together with Europe, the Appalachians and their northern continuation, the Adirondacks, join up with the Scottish Highlands. It's not just that they're both mountains, they're the same type of mountains with rocks of the same type and the same age. So again, kind of like putting together two pieces of a puzzle and finding out that your half blue flower on one piece matches another half blue flower on the other piece. The coal beds of Appalachia match up with the coal beds of Europe. They're the same age, the same type of coal. Up there at the top, those things labeled GY and S. GY is gypsum, that's calcium sulfate. If you powder it, you get plaster of Paris. And you can process that into sheetrock, for example. And gypsum deposits form in dry climates where mineral-rich water dries up. It's called an evaporite mineral. So does rock salt, and so does desert sandstone. And you get a belt of those about 200 million years old in the western US that actually matches with a belt of it found in Siberia. And if you look down, those things labeled GL, those are glacial deposits. When glaciers move over a continent, they leave very distinctive markings. The most recent glaciation gouged out a whole bunch of valleys and water-filled valleys and left these big bulldozed mounds of earth that they'd scraped up called moraines. And when glaciers move over a rock surface, they scratch it. And they leave these parallel scratches called glacial striations. You can see this today if you go to a place where glaciers are actively moving, like the coast of southern Alaska. You can find a lot of glacial striae. So yes.
Fjords were caused by glaciers, right?
Yeah, fjords are basically glacially carved valleys that have since flooded. As the Vikings used to say, have you raided a fjord lately? Okay, you guys don't remember when that was Ford's car jingle. Have you driven a Ford lately? And then, of course, the pious kids at the Baptist church wear these knockoff t-shirts that said, have you talked to the Lord lately? Anyway, I digress. So the point is, you can find ancient evidence of glaciers. And you not only know that glaciers were there, if you measure the direction of the glacial striae, the scratches that glaciers leave, you can tell what direction the glaciers were moving. And when you put the continents together that would make up Gondwana, not only do you have all these areas of ancient glacial deposits that match up, but the glacial striations all radiate out from where the South Pole would have been at the time, which is not where it is now. There's a common center that all of those striae are coming from, and that's what you would expect if the glaciation started at the coldest part of the world and spread outwards in all directions from it. That's not something you can easily explain with continents in separate locations. Wegener put this all out in a book called The Origin of Continents and Oceans. And he was mostly dismissed at first, simply because, as good as the evidence might seem, it sounds crazy that continents could freaking move, right? Because a continent is a slab of granite. In the case of North America, it's 3,000 miles wide and roughly 25 miles thick. That's a freaking big leaping slab of leaping rock. It feels really solid. How can something like that move? So Wegener was dismissed for a long time, and he didn't really get back into favor until the aftermath of World War II. The reason why it happened then was because submarines had turned out to be critically important in World War II. And if you're going to have a big submarine fleet, especially if you're going to put nukes on it, as we did, and other countries followed, you really, 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 really need to know what the bottom of the ocean looks like. Just, for the same reason that if you're going to have a navy on top of the ocean, you need really accurate charts of the coastlines, which is what the BIOL was doing back in 1831. For the same reason, if you're going to be piloting submarines, you don't want to run your very expensive nuclear submarine carrying probably the smartest people in the military. The nuclear navy is one of the most challenging branches of the military to get into. You've got to be a complete propeller head if you're going to run a nuclear reactor on a submarine. And if you're going to do that, you do not want to lose your submarine by crashing it into a rock that you did not realize was there. So there was a big surge of geophysical research into basically what the deep ocean is like. A lot of it was cover for military operations. This is probably the most famous. The Glomar Challenger was this ship that was set up to sail around and do research into the oceans and sample deep rocks and learn about the geology of the ocean floor. Its real mission was to fish up a Soviet submarine that had gotten wrecked and steal their code books, which in fact successfully did. They actually did not that easy. I mean, the sub was wrecked and it was in very deep water, but they managed to bring up about a third of a Soviet submarine. Fortunately, it was the part that contained the secret codes. But yeah, the cover was that they were doing deep sea research, and they actually did do a lot of deep sea research while waiting for the next sub to get wrecked. And all of this led to new understandings of where rocks come from on the bottom of the ocean and what the crust of the earth really is like. And by 1965, it led to the formation of modern plate tectonic theory. And I tell you what, it's 12:01. I really should keep talking for 10 minutes, but I really need to go to the bathroom. And I really need to sit down for a bit because my leg is not doing very well. And I'm sensing a slight sense of flagging enthusiasm in the room, all three of you. So I'm going to stop the recording.